Swayam Prabha. Digital India. Educated India.
Welcome to Basics of Noise and its Measurement. I am Nachiketa Tiwari, and this week we are having a discussion on transmission line equations and how these equations can be used to solve sound propagation problems in one-dimensional tubes. And today what we are going to do is apply these equations to solve for the nature of sound propagation in an open tube. So yesterday we had discussed a closed tube. Today we will have another example, and we will discuss how sound propagates in an open tube. So planar waves in 1D open tubes. So that's what we are going to discuss. So open tubes. So let's formulate the problem. Suppose I have a tube. And it is having a piston at one end. So this piston is getting excited by this crank mechanism, and let's say this is my x equals 0. So it has one open end at x is equal to 0. And the positive x is in this direction, and the length of the tube is L. So here at the other end where the piston is present, x is equal to minus L. And in the case of closed tube, we had said that we know the pressure at x equals minus L. Today we will make a little different assumption, that we will say that because I know how much piston is moving, so we know the value of us or the source velocity, because this is where the source of sound is. So we know the velocity at the source. So velocity at minus L at any time is given as some constant us. This is a real number, cosine of omega t plus phi. Okay. So this is the velocity at x is equal to minus L. So once again we have two boundary conditions. There is an open tube at one end of the tube, and then there is the other end, x is equal to minus N, where we know the source. Now at the open end, we know, because the end of the tube is open here, we have to now convert this physical situation into some mathematical relationship. So we know that the ambient pressure here is P naught. Okay. The ambient pressure here is P naught, because you have the overall atmosphere is there. It's a big, so it's P naught is there, and inside the tube at all points we have P naught plus P as a function of x and t. So the pressure inside the tube is P naught plus small perturbation in pressure, that is lowercase p, which varies with x and t, and outside the tube the pressure is P naught. And what that means is that as I approach this boundary, then the magnitude of P has to become less and less, and at the boundary P of 0 and T should be 0. So, this is one boundary condition from a mathematical standpoint, that when you have an open tube at its open end, in this case the open end is at x equals 0, the value of P, which is the perturbation in pressure, is 0. And then the other boundary condition is this one, and this says that I know the value of velocity, particle velocity at x is equal to minus L, and that is same as the velocity of the piston, which is us cosine omega t plus phi. So, these are the two boundary conditions, and just like we solved for those 4 variables in case of 4 unknowns in case of closed tube, we again have 4 unknowns, 2 equations, and then the 2 extra conditions are these 2 boundary conditions. So, once we apply these 2 boundary conditions, we get the solution for the system. So, we will do the same thing or a similar thing which we did in the case of closed tubes. So, so my transmission line equations, we begin by writing these transmission line equations. And that equals so these are general transmission line equations which are valid for all 1D planar flow situations. And now we are going to apply these boundary conditions, and we will get transmission line equations which are specific for closed tubes. So, we apply the first boundary condition at x equals 0, and at x equals 0, P of 0t equals 0. So, when I put this equation in the first in the equation for pressure, then what I get is P of 0t equals real of P plus, and E minus j omega x over c at x equals 0 is 1. So, it is not there, and then I have plus P minus times E j omega x over c, again since x is equal to 0, E j omega x over c is 1. So, this is there E j omega t, and this is equal to 0. And this is possible only if P minus, so this gives us the condition that P minus has to be equal to minus of P plus. Okay. So, I put this condition back in my transmission line equation, and I replace P minus with negative of P plus. So, I am left with and here I get a positive of P plus. Okay. So, now I have used one of my boundary conditions, and what I will do is I will again rewrite these equations, and this is equal to real of P plus E minus j omega x over c plus, oh excuse me, minus E j omega x over c E j omega t. So, this is the equation for pressure using this modified transmission line equation, and the equation for velocity is real of P plus over Z naught E minus j omega x over C plus E j omega x over C, E j omega t. Okay. So, these are the transmission line equations for open tube. Doesn't matter what is the condition at the other end where the piston is moving back and forth, but as long as this end is open, these equations are good. And now again we use the second boundary condition, but before we do that we will simplify these equations further. So, we know that E j omega x over C negative minus E j omega x over C, and this equals minus 2j sin omega x over C. Similarly, we also know that E minus j omega x over C plus E j omega x over C, actually I am going to make this a little clearer, this equals 2 cosine omega x over C. So, I put these expressions back in these two relations. So, my expression for P x t becomes real of P plus 2j sin omega x over C E j omega t. Okay. And my expression for U simplifies to real of P plus twice of P plus cosine omega x over C times E j omega t. And then of course, I have to multiply by this by 1 over Z naught. So, these are my modified transmission line equations for an open tube. And to calculate the value of P plus, I use the other boundary condition which exists at x is equal to minus L and get the value of P plus, and that is what I am going to do. So, we know, so now we use B C at x is equal to minus L, and which is that U minus L t equals some real number US cosine of omega t plus phi, and this I can write it in complex format as nothing but real of US E j omega t plus phi, right, and this can be further modified as US E j omega t times E j phi. Okay. So, let us call this equation A1, let us call this equation A2, and let us call this equation A3. So, what we do is we put A3 in A1, A2, and we solve for P plus, and that is what we are going to do now. So, on the, so this thing, it goes on the left hand side. So, what I get is real of US E j omega t E j phi equals real of 2p plus cosine, and here the value of x is minus L and cosine of omega, cosine of minus omega L over C is same as cosine of omega L over C. So this becomes cosine of omega L over C E j omega t times 1 over z naught. Okay. So if these two sides have to be equal, then the terms in the parenthesis have to be same. So I can drop this expression real, and then e j omega t and e j omega t cancel out, and what I am left with is that p plus equals u s times z naught divided by 2 cosine of omega L over C. Yeah. So this is my A4. Okay. And now what I do is I plug equation A4 in A1 and A2 to get expressions for pressure and velocity. So what we do is now is plug A4 in A1 and A2 to get expressions for u of x and t and p of x and t. And if we do all that, and if we do the math carefully, then what I am going to do is I am going to write down the final relations. Then the final relations look like this. So pressure is nothing but Qs z naught over cosine omega L over C times sine omega x over C times sine omega t plus phi, and u of x and t is equal to us z naught over cosine omega L over C times cosine omega x over C cosine omega t plus phi. So once again, so these two equations represent propagation of sound in an open tube, and these are the functions for pressure and velocity. And as we saw in the case of closed tube, here also we have standing waves, but the difference is that in the case of closed tube, the standing wave for velocity had a value of 0 at the closed end, and in this, and the pressure was maximum. In this case, the pressure at open end is 0, so it is minimum, its amplitude is minimum, but the velocity is maximum at x equals 0. So this is the fundamental difference between these two standing waves. So this closes the treatment of an open tube, and thanks for listening to this lecture, and I look forward to seeing you tomorrow. Thank you very much.